In this video, I'm going to share some secrets. And they're not really secrets, they're more just common sense. But they're going to be tips that you can use and things that you can do to become really good at eddy current data analysis. Now, this is going to pertain specifically to tubing data analysis using the impedance plane phase analysis process, but you can do similar things with surface testing. Now, one of the first things I want to talk about is calibration tube. ASME calibration tubes contain specifically machined defects such as flat bottom holes. We got some groove wear on this end. Where's the groove wear? Here we got an OD groove, and most of the rest are just flat bottom holes in this particular cal standard. Then I've got a cal standard here that's got some 360 degree, where is it? Yeah, here we got some 360 degree wear scars of different depths. But these calibration tubes, like I say, they're made in a machine shop and they have pretty much perfectly designed flat bottom holes or grooves that are very symmetrical. And calibration tubes aren't made to teach you how to do data analysis. They're made to calibrate your system or standardize your system, as they say in Australia, to known flaws so you can set up the phases of your different flaws and your spans. And you can also use something like the 20% flat bottom holes to set your voltage. You also use those signals to set up phase versus depth or amplitude versus depth sizing curves for things like pits or wear. But the perfectly machined cal standards don't really prepare you for what you're going to see in an actual tube. Now, for anybody that's looked at tubing data, I've got some here on my screen, you're going to encounter all sorts of signals that look nothing like what's in your calibration standard. That's a good example. You'll never see this in a calibration standard. Let's look at channel 5. There's a bunch of squirrely stuff going on in there. And if you've never seen it before in a calibration standard, you have to apply the knowledge and the rules that you've learned throughout your data analysis training to sort of deduce what's causing these signals. Now, I've often said that a good data analyst has several traits or characteristics. One of them is they got to have a little bit of common sense. Number 2, very important, you got to look at lots and lots of real data so you can recognize patterns that are normal and patterns that are abnormal. And I think one of the most important things that helped get me a long way in my career was having curiosity. So in the early days, when I was a young data analyst, about 30 some years ago, I would always listen to level 3s explain what they thought a specific signal was, and they'd talk about phase changes between the frequencies, and they'd talk about how different types of material will have a different effect on your impedance trajectory and amplitude. And a lot of times I think they were just talking out of their rear end, and I'm like, how do they know that? I've studied all the same stuff they did and probably more. I got every certification you could possibly get in eddy current testing, at least for tubing. And I was still perplexed at many of these signals. Like, what causes a signal to look strange like that? Or what gives you multiple signals with varying phase angles like this? Or what about this thing that gives you this elongated kidney bean shape? And what I did to satisfy my curiosity was I got about a 5-foot long piece of Inconel tubing here, and I took it into my garage, and I had a Dremel tool, I had some drill bits, I had some emery paper, I had a couple different types of, I had a grinding wheel, I had a blowtorch, And I would just introduce a hacksaw. There's a hacksaw blade right there, diagonal. So, you don't see too many diagonal flaws in a heat exchanger tube, although you could if you had some foreign object or foreign material in there wearing at your tube OD at an angle. And I've got some scratches in here somewhere. There's a bunch of scratches. I did that with the head of a screwdriver, I think. And obviously I didn't take great care making this cal standard. I just wanted to make a bunch of, different types of flaws. And a lot of these, you'd never see something like this. These are just a bunch of grinding wheel impacts. You're not going to see that in a heat exchanger. But after this, you're going to see what things like this will give you on the display screen. Here I've got a fairly deep, maybe a foreign object wear, and then I got some tapered wear. But one thing that's different when you make a standard like this, and you play around with it, and you've got your tester in hand, your probe in hand, and you're able to hold the tube and look at the tube, you can see exactly what's causing what you see on your screen. One of the problems when you're inspecting heat exchanger tubing is you usually don't ever see the tube. The most you can see is the hole at the end of the tube where you put your probe in, and that's it. Unless you get some crews to go in on the secondary side and go into the tube bundle with a camera, that's the only time you're going to be able to see what's actually going on in the tube. Now, a lot of times if you get a strange signal, you'll actually ask the customer, do you have a borescope where we can go look at this? Because this is strange and I haven't seen it before. But that all takes time and money and it's expensive. So you don't often get the opportunity to do that. But when you have your own free time and your own shop, and if you can get a piece of tube and you got a bunch of tools, you can create something like this so you can explore what types of flaws cause what type of signatures. So, just starting off, I drilled a small hole similar to the size hole that's in an ASME cal tube. And that's what shows up at the bottom of your screen here. Notice how I calibrated it on a couple different differential channels. 100% hole at 40 degrees. And then I got a couple absolute channels over here. And then the next thing there, I think that's just some sort of polishing wheel, which obviously didn't introduce any sort of flaw. There's nothing there. Then I've got some sort of buffing wheel here, which, let's see what that is. It could be that. Obviously that must have had some abrasive quality to it because it did introduce an OD flaw. Notice that rotates counterclockwise with decrease in test frequency. Also, the absolute signals are very pronounced. Then we've got some tapered wear right here. Now notice the difference between, this is the hole, it's got some certain axial length to it here. And when we get up to this guy, it's a little bit wider. That's because these two flaws that I introduced have a little bit of width to them. Then it looks like we've got some little stuff going on in here. I gotta figure out where that is. Even when you're holding the tube in hand, sometimes it's hard to figure out exactly where you're at. And then I've got some scratches. And then I've got, I got a pretty shallow, it's hard to see these on the camera, I got a pretty shallow flat bottom hole drilled in there. Then, the next thing is I think this diagonal hacksaw cut. No, that's not it. The hacksaw cut's going to be wider. Maybe that's the hacksaw cut right there. And then I've got a circumferentially oriented hacksaw cut fairly deep. So notice how, even though it's circumferentially oriented, you can get these huge signals. That's because they have some width to them, or to the bobbin coil, it's got some axial extent. And when I get up in here, there I got some, see that funny shape there? That's a tapered wear. It's much deeper on one end and shallower on the other end. There's the deep end, there's the shallow end. Then I've got another tapered wear right in here. Then I started getting a little bit crazier with the tooling. This is going to be the multiple grinding marks, which is what you see right here. So notice all of the different phase angles in that area. That's because there's a bunch of different flaws with different depths. Now, I didn't make a sizing curve on here, but if I did, if I made a phase versus depth curve, all these different angles would give you different depth estimates. So as I scroll through this data, there's probably one flaw, there's another flaw right in the middle there. So you got 1, 2, 3, 4 maybe. You got one that's real deep in there. See that right there? That little vertical spot. That's probably the deepest area in this whole little cal tube here. That's probably 60 or 80% deep. Then, after that, I've got a real deep, little bit of a taper to it, but that's really, actually looks quite deep when I look at the tube wall. But when you look at the phase angle, that's probably only about 20, 30% deep, something like that. Then I took a buffing wheel, some sort of abrasive wheel, and made some scratches. And then in the middle of it, I put another one of those deeper wear flaws in there. Now, what's interesting about this one is you've got two distinctly different phase angles going on here. The shallow, or the high phase, indicating shallow percent through wall depth, is probably from the buffing wheel, the abrasive wheel there. And then right in the middle of all that, you've got this thing that's very deep. So that's probably close to 100% there, not quite all the way through. But when you have multiple things going on in your tube, you can get multiple different phase angles at the location. You would call this sort of a complex signal because you got more than one thing going on there. Then towards the end, I've got a slight area of some more buffing, followed by an OD, kind of like a flat bottom hole right towards the end here. So once again, you're not going to see anything like this in an ASME tube because you just have flat bottom holes and some grooves. And then if you have a calibration standard for doing array, you might have a spiral groove in it to check your, make sure your probe's wired directly and your configuration's correct and all your channels are firing in the right order. But again, perfect calibration tubes like that are meant to calibrate your system and to periodically check your system, make sure that it hasn't drifted and that everything's still operating correctly. But those simple signals will not really teach you how to do data analysis. What you have to do is, if you're curious about something, mock it up, make your own tube. Now, a while back, I was reading something about the effect that different diameter holes would have on the eddy current signals. So what better to do than take a piece of 9010 copper nickel tube and make a bunch of different holes of varying depths of different diameters. So you can observe them that as the diameter gets larger, the phase will drop down towards the horizontal. Now, you're never going to see anything like this in a real heat exchanger, hopefully not, right? But it's a lot easier to learn from something you made in your garage than it is by looking at a cal tube made in a shop. Now here, I've showed you some examples of things that I use for tubing, but you can also make a lot of calibration standards for doing surface testing, especially when you want to play around with multi-frequencies and how different types of flaws look at different layers within your test piece. So I have boxes full of samples I use for surface testing made out of a variety of materials with a variety of thicknesses and a variety of different simulated flaws. So when you're curious like that and you take the time to make your own samples, it will take you a long way when it comes to properly evaluating data. Thanks for watching.